Here we go with the last of the 4 videos for the great blizzard of January 27th, 2015. This result concerns a very special type of function. It's a function g of x and y that happens to be the product of a function of x, f1, and a function of y, f2. It's amazing, though, how many of the integrals that you have to evaluate actually turn out to be a sum of functions of this form. Let me start with an example and then show you how to do the proof. So for the example, the function in question is going to be x squared times sine y. That's clearly a function of x times a function of y, and we're going to be integrating it over a rectangle that extends in x from 0 to 1 and that extends along y from 0 to pi. And what the theorem says, which we are about to prove, is that we can evaluate that integral by taking the integral of f1, that's the function x squared, from 0 to 1, and multiplying it by the integral of f2, the function sine y, from 0 to pi. This is so obviously the way to evaluate the integral that it's a bit of a surprise that we can actually prove it. But first, let's do the calculation. You all know how to do integrals in one dimension. We take the antiderivative of x squared, evaluate it between the limits 0 and 1. We take the antiderivative of sine y, which is minus cosine y, evaluate that between the limits of 0 and pi. So we get 1/3 minus 0 from the integral over x. We get minus 1 plus 1 from evaluating minus cosine y at the two limits, and that gives us 1/3 times 2, so the integral is 2/3. I put a little R script on the website to show you how, by using a function that's in the practical math library, you can check this numerically, and you might want to use the technique in that R script to check your numerical answers for some of the integrals you'll be doing in section. Using R to evaluate double integrals doesn't really teach you anything about double integrals, but it's a nice way to check that you haven't made any mistakes in arithmetic. Okay, let me quickly run through the proof, and then I will write it out. The cubes that we want to use for g are going to be products of cubes for f1 and cubes for f2. And if n and m are both equal to 1, a cube, so-called, for f1 is just an interval along the x-axis. A cube for a2 is just an interval along the y-axis, and the correct name for that cube is a1 cross a2. It's the Cartesian product of the set a1, an interval, and the set a2, an interval. Now, this theorem is simple to prove only in the case where f1 and f2 are non-negative, because in that case The way we get the maximum value of g on this cube is by choosing a value of x for which f1 has a maximum. Perhaps, for example, f1 is an increasing function of x, so it achieves its maximum on the right-hand boundary. And then we choose a value of y for which f2 has its maximum. Maybe f2 gets larger and larger, achieves a maximum here, and then starts getting smaller and smaller. So it follows that the largest possible value for g on this cube is equal to the supremum of f1 over a1 multiplied by the supremum of f2 over a2. If f1 and f2 were both negative, this wouldn't necessarily be so. It could be that on a1, f1 achieved a very large negative value. f2 on a2 achieved a very large negative value. The product of those very large negative values would be a very large positive value, so that the supremum of g would actually be the product of the infimum of f1 and the infimum of f2. You'll be dealing with that situation on the homework. Now there's a general principle of doing proofs that applies here, namely that it's almost easier, always easier, to expand than to factor. So I'm going to write out the upper Riemann sum for f1 and the upper Riemann sum for f2 and multiply them together. To get the upper sum for f1, we want to add up the supremum for all the cubes, and I guess I really should multiply this by 1 over 2 to the n raised to some power. Same thing here. When I multiply together those upper sums like that, I get a sum of terms where I'm summing over individual cubes like this one, and I suppose that I really should be multiplying by 1 over 2 to the n raised in general to the nth power times 1 over 2 to the n raised to the mth power. But in any event, what I get is just the sum over these Cartesian product cubes that defines the upper sum for g. So the upper sum for f1 multiplied by the upper sum for f2 is equal to the upper sum for g. A similar argument shows that the lower sum for g is the product of the lower sum for f1 and the lower sum for f2. But now f1 and f2 are integrable functions. That means in the limit where n approaches infinity, the lower sum and the upper sum both approach a common limit, which is the integral of f1. Same thing is true for f2. The lower sum and the upper sum approach as a common limit the integral of f2. And therefore, the lower sum for g and the upper sum for g both approach a common limit, which is the product of the integral of f1 and the integral of f2. But the common limit of the lower sum and upper sum for g is what we mean by the integral of g, and that completes the proof. If you are not allowed to assume that f1 and f2 are non-negative, then this proof becomes a little bit messier, and I've given that to you as a homework problem. Warning, as I said before, if f1 and f2 can be negative, and on a specific cube they are both negative, then it's entirely possible to have a situation where the maximum value of G is equal to the product of the minimum values of F1 and F2. So that's going to be the first part of your proof. The second part of the proof involves proving that the volume, which in the one-dimensional case is just length, of the interval from A to B is equal to B minus A. You might have said, isn't that the definition of length? But no, our definition of length is for a set A, it's the integral of the indicator function of that set that defines the volume. So we can say that the interval that extends along the x-axis from 0 to 1 has a one-dimensional volume of 1. Incidentally, it has a two-dimensional volume of 0 because I can enclose it entirely in a set of squares that have as small a combined volume as I like. Following the textbook, we will say that if a set A has a well-defined volume, we'll call it pavable. And now we're going to prove that the interval from A to B is pavable and its one-dimensional volume is equal to the difference B minus A. Let's consider a concrete example. The interval that extends from A equals the square root of 2 to B equals 5/3. Let's first take capital N equals 2. We only need one dyadic cube, the one that extends from 1 to 2 at level 0, but at level 2 we have to break this up into 4 pieces. First we split it in the middle, then we split each of those cubes again, and the square root of 2 lies in the second of those cubes. 5/3 lies in the third of the 4 dyadic cubes. So there's a graph of the indicator function for the interval from A to B. It's 1 for values of x between the square root of 2 and 5/3. It's 0 everywhere else. And if you look carefully, you will notice that at level capital N equals 2, the infimum of this function is 0 on all 4 of these cubes, but the supremum of the function is equal to 1 on the middle 2 cubes, 0 on the outer cubes. So in that particular case, the upper sum is 1/2, the lower sum is 0. Now let's consider what happens for a large value of n. We'll move along the x-axis. Here is A, which is the square root of 2. And it's going to fall in some dyadic cube that has an upper boundary, which I'll call A sub n. Here is B equals 5/3. That's going to fall in some dyadic cube that has a lower bound, which I will call B sub n. Now think about all the dyadic cubes between 1 and 2. There will be lots of them where the contribution to the lower sum is 0 and the contribution to the upper sum is 0. There will also be lots of them in between a sub n and b sub n, where our indicator function has the value 1 and contributes the same amount both to the upper sum and the lower sum. It's only the two cubes around A and B that contribute differently. Those two cubes contribute 2 over 2 to the n to the upper sum, but they contribute nothing to the lower sum. So, the difference between the upper sum and the lower sum is 2 over 2 to the n. That approaches 0 as n approaches infinity. That means the indicator function is integrable, that this set, the interval from a to b, is a pavable set, and we can now evaluate the integral of the indicator function, the length of the interval, by taking the limit of either the lower sum or the upper sum. I find it a little bit easier to do the lower sum. The lower sum is just the total volume of the cubes where the infimum, m sub c, is equal to 1. The total volume of those cubes is the total volume of all the cubes from a sub n to b sub m. It's b sub n minus a sub n. That's all you really have to say, though you might want to indicate that b sub n is going to be some integer over 2 to the n, while a sub n will be some other integer over 2 to the n. Let's take the limit as n approaches infinity of L sub n. That's the limit of b sub n minus a sub n. As you proved last term, that's the limit of b sub n minus the limit of a sub n. But these cubes are getting smaller and smaller and smaller. Clearly, a sub n is a decreasing sequence that approaches a. B sub n is an increasing sequence that approaches b. So we get b minus a, and our result is proved. If we go from one dimension to 2 dimensions, we have to combine the two results we just proved. We say, if we've got a rectangle A that extends along x from A1 to B1, and that extends along y from A2 to B2, the volume, our generic term for what in 2 dimensions we usually call area, is the integral of the indicator function with respect to x and y. That indicator function is clearly a product of a function of x that's 1 from a1 to b1 and a function of y that's 1 from a2 to b2, and we know what the integral of each of those functions is. For x, we get b1 minus a1. For y, we get b2 minus a2. And we have proved that the area of a rectangle is equal to the product of its width and its height. Okay, let's do this over again from scratch. And while the book states this result where x is an n-component vector and y is an m-component vector, for purposes of drawing pictures, it's convenient to assume that n and m are both equal to 1. So let me do my best to draw this picture. We'll run x that way. We'll run y that way. For sake of concreteness, let's assume we have 4 cubes for x, 4 cubes for y. So here are our cubes, really just intervals for x. Here are our cubes for y. Our functions f1 and f2 are functions of x and y respectively. And the cubes for g are the Cartesian products of these. We got 4 cubes for x. We got 4 cubes for y. And we got 16 nice little squares here. If this cube is called A2 and this cube is called A1, the appropriate name for that cube is A1 cross A2. It's the Cartesian product of 2 sets. This interval along the x-axis and that interval along the y-axis. Now, f1 and f2 are non-negative. In that simple case, the supremum of the product g, which is f1 times f2 over this cube, is equal to the product of the supremum of f1 over a1 times the supremum of f2 over a2. Evaluating integrals of a function of x and y that's not a product of a function of x by a function of y is substantially trickier. We'll be taking that up next week. Okay, it's always easier to expand than to factor. So let's take the upper sum for f1 and multiply it by the upper sum for f2 and see what we get. We're going to be summing over cubes. Using the same notation as in the textbook, I will use generically C1 to denote a cube at level n along the x-axis. The volume of such a cube, i.e. the length of the interval, is 1 over 2 to the n, and we have to multiply that by the supremum over the cube. Then doing the same thing for f2, we're summing over cubes called C2, which are dyadic cubes in R along the y-axis. And for the upper sum, we get the volume, i.e. the length of one of those cubes, times the supremum of f2 over that cube. And when I multiply these two things together, I'm summing over cubes that are Cartesian products, like that. And those are going to be dyadic cubes in R2. I will have 1 over 2 to the n squared times the supremum of f1 over c1 multiplied by the supremum of f2 over c2, or if you prefer, I'm summing over these Cartesian products the volume of a cube, that is the area of one of those little squares, times the supremum over that square of G, and that's exactly what I mean by the upper Riemann sum for G. That was tedious enough. I'm not going to write out the details of the similar proof for the lower sum, a proof that works exactly the same way using infimum rather than supremum, shows that the lower sum for f1 times the lower sum for f2 is equal to the lower sum for G. Now let's let capital N approach infinity. f1 is integrable, so its lower sum and its upper sum both approach its integral. f2 is integrable, so its lower sum and its upper sum both approach its integral. The lower sum for G is the product of these two. The upper sum for G is the product of these two, and therefore the upper and lower sums for G approach the same limit. It follows that the product function G is integrable, and the value of that integral is equal to the product of the integral of f1 and the integral of f2. Okay, that's part one of this longish proof. Now let's go on to the next part. A and B are arbitrary real numbers. Think of them as being irrational because that's the interesting case. And A is assumed to be less than B. What we want to prove is that the integral of the constant function 1 from A to B is equal to b minus a. If we didn't use dyadic cubes, there'd be nothing to prove here. However, since we've chosen to use dyadic cubes to define integrals, because that's the only definition that extends neatly to Rn, this is a provable theorem, and here's how we prove it. Let's look at what's going on when we evaluate the integral of the indicator function. The indicator function for this interval from a to b is, of course, the function that equals 1 between a and b and 0 everywhere else. Now, a is going to lie in some dyadic cube. And let's denote by a sub n the upper endpoint of the dyadic cube that includes a. Let's denote by b sub n the lower limit of the dyadic cube that includes b. In between a sub n and b sub n, there are cubes that contribute equally to the lower sum and the upper sum for this function, which is the indicator function for the interval from a to b. Here, there are going to be a lot of cubes that contribute 0 to both the lower and upper sum, and up here there are going to be a lot of cubes that contribute 0. So there are only two exceptional cubes. This cube contributes to the upper sum but not to the lower sum. So does that one. And it follows that when we calculate the difference between the upper sum and the lower sum, it's going to come entirely from those two cubes. There are going to be two of them. Each has a length 1 over 2 to the n. And this comes entirely from the two cubes that contain a and b. Since this approaches a limit of 0 as n approaches infinity, the indicator function for the interval from a to b is integrable. Once we know that a function is integrable, we can take our choice, either take the limit of the lower sum or the limit of the upper sum. So the lower sum at level n of dyadic subdivision is b sub n minus a sub n, right? The sum of the lengths of all the intervals from a sub n to b sub n is just b sub n minus a sub n. Since b sub n and a sub n are dyadic, you might want to point out that each of these is going to be some integer divided by 2 to the n. Now let's think about what happens as n approaches infinity. As n approaches infinity, a sub n approaches a. Because these cubes get smaller and smaller, this is in fact going to be a decreasing sequence. B sub n is always less than or equal to b. It's going to get larger and larger. It's an increasing sequence. Oh dear, dear me. I've done it again. How do I get rid of that box? Ah, saved by the escape key. And now we're done. The limit as n approaches infinity of this lower sum for the indicator function is equal to the limit of b sub n minus a sub n, but as we proved last term, that's the limit of b sub n minus the limit of a sub n, which is equal to b minus a. And we've done it. We've proved that with our dyadic cube definition of integral and the definition of volume as the integral of the indicator function, the length of the interval from b to a is exactly what you'd hope. It's equal to b minus a. And now we can finish it off by combining the two results we've just proved. We've got a rectangle that extends in x from a1 to b1, that extends in y from a2 to b2. So there's our rectangle. The indicator function for this rectangle is clearly the product of the function that's 1 when x is between a1 and b1 times the function that equals 1 when y is between a2 and b2. So the theorem we proved about product functions applies. And the integral is equal to the product of the indicator function for the interval from a1 to b1 along x times the indicator function for the interval from a2 to b2 along y, which, by virtue of what we proved at the top of the page, is b1 minus a1 times b2 minus a2. So, our definition of volume in general, which works in Rn, has the reassuring property that in R2 the area of a rectangle is the product of its two dimensions. And having got this far, I think I can conclude with a little song. The proofs are completed, so let it snow, let it snow, let it snow.